Hello, welcome to MasterJack Computing. In this series of video, we are going to go through Chapter 1, Information Representation. And in this particular video, we are going to cover the internal coding of images. Previously, we have already discussed the internal coding of numbers and text. Today, we are going to talk about another type of information, which is images. In general, images can be divided into two subcategories. The first one is vector graphic, and the second one is bitmap. What is the difference between them? Well, let's have a real-world example. In a moment, I'm going to show you two pictures with the exact same content, one stored in vector graphics and one stored in bitmap. What I want you to do is to have a look on what happens when I enlarge both of these photos. So this is a photo of the vector graphic file. Let me enlarge it to this left-hand side corner element, 100% bio. And now I'm going to do the same thing on the bitmap image. Right, so this is a bitmap image, and this is a vector image. Can you see the difference? As we can see clearly, the vector graphics quality remained the same after scaled up. However, on the other hand, bitmap, the quality dropped significantly as image scaled up. But why is this? It is because fundamentally, they store data in different formats. Vector graphics, it stores lines and shapes. If we see the graph on the right-hand side corner, this one, we can say it stores the lines equations and the equation of the circle and the equation of a parabola. So it stores equations and the lines. However, on the other hand, bitmap, it stores individual pixels, which is a small square in this case. So it stores 1,000,000 square in one line and maybe 1,000,000 square in a vertical line, and this way it composes up the image. When we scale up a vector graphics, what the computer do is it recalculates every single point of the line and that circle. So it will still be a perfect circle. However, when we enlarge the bitmap, the computer don't know because it only knows the pixel. When we scale up, there are less pixels in total in the area, and the computer has to guess what color it is for the pixel next to each other. That's why it gets blurred. Well, how vector graphics avoids distortion? Like what I just said, the dimensions of the object are not defined explicitly, but instead are defined relative to an imaginary draw-in canals. What that means is the imaginary draw-in canals is divided into an x and y axis with coordinates on them. Each time we zoom in the coordinates, which means we change the smallest division scale on the axis, and all the coordinates are being recalculated and redisplayed on the graph. So, wherever the image is to be displayed, the file is read, the appropriate calculations are made, and the objects are drawn to a suitable scale. This avoids image distortion, such as an image being squashed or scratched. So how does computer store vector graphics? Well, the vector graphic file contains a drawing list, and this list contains a command for each object. And a command has a list of attributes. So, for example, a command could be drawing a circle here with certain attributes to the circle. The attributes defines a property of the object, and properties include shape, color, and size. Sorry, this should be a size here. So shape, color, and size. For example, I want a circle with a center at 0, 0, with a radius equals to 2. And that is some property, where all of these geometric objects forming a drawing list, and that will make a vector graphic. So in summary, the vector graphics file is used for images consisting of geometric objects such as lines, circles, and also parabolas. Dimensions are defined relatively, so each time we scale up the image, the coordinates will be recalculated, and that means the image can be scaled without loss of quality. So in order to remember these, we're going to build up connections between these points. So it is geometric objects, which is lines and circles. So lines and circles, they can be defined with radius and also the center of the circle, for example. That means the dimensions are defined relatively to the canals. And since the dimensions are defined relatively, the image can be scaled up without loss of quality. Right, let's move on to the other type of image called bitmaps. Bitmap is the most common picture type that you stored on your phone. So these photos are me traveling in Beijing, taken by my phone, which has an extension of .jpg, and these are all bitmap formats. So for the bitmap, a PNG, JPEG, or GLF all contains pixels as the smallest component. So bitmap is composed of millions of pixels. The pixel is the smallest component, usually a square. So say for example, this blue circle shown here is 1 pixel. So I'll give you 5 seconds to think about how many pixels are there in this photo. Well, clearly there are 8 pixels per line and then 8 pixels per column. So it's 8 times 8, which is 64 pixels in total. However, we usually written the pixel count with the line and column with a multiplication form, which is 8 times 8 instead of 64. And this 8 times 8 also means an image resolution, which is how clear the image is. So if we have more pixels per row and more pixels per column, that will make the image more clear. And or we can say an image has a better resolution. So this slide we introduce a new concept called image resolution. It's a total number of pixels, which is usually represented by pixels per row times pixels per column. And the image resolution influence. The higher the resolution, the more pixels available, and therefore the crisper the picture. Say, for example, we got 2 apples here, and the left-hand side one has a more pixel counts, a higher resolution, more pixels per row and more pixels per column, and that apple looks more crispy. It is definitely more delicious compared to the one on the right-hand side. Well, in order to project a picture onto a screen, we also need to take screen resolution into account, because basically the screen is also made up of pixels. So the screen resolution, typically an old laptop, it could be 1024 times 768. That means 1024 pixels per row and then 768 pixels per column. If you watch YouTube, sometimes you know how to change the resolution from like 720p, for example, to 1080p or the 4K. So the 1080p is the one we're more familiar with, which has 1920 pixels per row and 180 pixels per column. That's why it's called 1080p. You can also see the resolution of your monitor with the settings if you're using the Windows screen. So if you go to settings and then you go to the monitor settings, and you will see the resolution of the monitor of mine is 1920 times 1080, which means the maximum screen resolution that I can play is a 1080p HD video. Right, we don't want to see black and white images, do we? But how to make the picture more colorful? Well, to do this, we need to store color for each pixel. And this introduced me to the concept of color depth, which is the number of bits to store one pixel is called color depth. So how many bits could be used for the color depth of these photos? Well, let's see the left-hand side one first. How many colors are there? Well, clearly we only got white and black, which is 2 colors. So if we have a 1-digit binary, it will have 2 different unique values, which is 0 and 1. And if we use 0 to represent black and we use 1 to represent white, that will be perfect for this scenario. So that means the color depth for the left-hand side image could be 1 bit. Let's quickly go through what we did. We count how many colors there are in the picture, and then we think about how many bits there are. So for a 1-bit binary, we got 2 combinations, that's 2 colors. Well, you may pause the video here to think about what will happen for the right-hand side one. Right, let's go through this together. For the right-hand side one, we can clearly see we got white, black, yellow, and red, which is 4 colors. So we know 1-digit binary, it have 2 unique combinations, and if we add 1 more digit to it, it will be 2 times 2, which is 4 unique combinations, which is 0, 0, 0, 1, 1, 0, and 1, 1. That's 4 unique combinations with 4 colors. Perfect. So for the right-hand side images, we need a color depth, a minimum of 2 bits. Right. There are also other ways to define color. Previously, we defined color by pixel. However, in physics and art, we also know that all colors can be obtained from red, green, and blue. And all these colors are called primary colors. Say for example, if we mix red and green, we can get this yellow color, and if we mix red and blue, we can get purple. So there's another way of defining the color of each individual pixel with bit depth. Bit depth is the number of bits used to represent each of the red, green, and blue colors. On the right-hand side, say for example, we get 8-bit to represent red color, which allows 256 unique combinations, which is 2 to the power of 8. We have 8-bit for the green color and also 8-bit for the blue color, and this will give us around 17 million combinations of color. So for each individual pixels, we say 8-bit to store red, 8-bit to store green, and 8-bit to store blue. So what is the color depth of this image? Well, if your answer is 24, I would say well done, because each individual pixels is made of 8-bit of red, 8-bit of green, and 8-bit of blue. So 8 plus 8 plus 8, which is equal to 24. So the color depth of this image is 24-bit. Perfect. And bit depth is actually a very useful concept in a lot of software. Say for example, the one shown here is my Samsung Note. And as we can see clearly, we got a red, we got a green, and we got a blue. And all of these colors are using the bit depth notation. So I have a value of 255 for red and 54 for the, I can't see very clearly. Just give me 1 second. 54 for green and then 54 for blue. Right. Well, let's draw a quick summary about bitmap. So, pixel has a defined color and position. Bitmap is made out of pixels, which is the smallest unit within a bitmap file. And the bitmap image has a defined resolution, which means how many pixels per row and how many pixels per column. And finally, it can be scaled, but the quality is affected. Like what we've shown earlier in this video, we can see the pixels can be scratched, however, you get blurred. Well, yeah. Let's go through this example on the textbook, which talks about bitmap and file sizes. File size is important because when we are copying a picture from one place to the other, we have to know how large the photo is in order to make sure it can be copied correctly into a USB drive or not exceed the limit of the cloud. So you have been asked to calculate a value for the minimum size of a bitmap file. The bitmap is to use a bit depth of 8, and the bitmap is to be printed with 70 dots per inch and to have a dimension of 5 inches by 3 inches. We use information provided about the color depths or the bit depths or blah blah blah. Okay, so basically the first 2 lines of the question. I'll give you 5 seconds to think about it. Right, so for a bitmap file, we read as we go through. It has a bit depth of 8, which means it has a color depth of 8 plus 8 plus 8, which is 24. So that image will get a color depth of 24, which means each individual pixel will take 24 bits. And then the bitmap file is to be printed with 72 dots per inch, which means 1 inch, it will get 72 dots, or we can say 72 pixels. And also have a dimension of 5 inches times 3 inches. So how many pixels are there in a horizontal line? Well, it's easy to work out, which is 5 times 72. What about how many pixels per column? Right, it's 3 times 72. And this gives us the total number of pixels in the image if we time these two up. And finally, if we time the bits per pixel, which is a color depth, and then we'll get the smallest size of this bitmap image. Right, here's what the textbook is doing. 5 times 72, number of pixels per row, 7 times 32, number of pixels per column, times them together, total number of pixels, multiplied by 24, and then we got this number of bytes, which is a little bit hard to read. So instead of displaying this byte number, we divide it by 1024 and change it to kibibyte. Perfect. Well, now we get a question of how images are being stored. I took the same 2 photos at the same place with different camera. Which one do you think have a better quality and why? So for the first photo, I have this one, which is a 7.1 megabyte, and the second photo with a different camera, it only takes a 50 kibibyte. So which one has a better quality? Well, obviously, the one that took more storage units will have a better quality because there are more data in it. But why does it have more data in it? Let's have a look and see why that is the case. Now, let's have a look on what's the influence of file sizes on the quality of image. The left-hand side one is a 7.1 megabyte image, and the right-hand side one is a 50 kibibyte of the image. And for the 7.1 megabyte of the image, if I zoom in, we can see it is still pretty much clear of the face and everything. However, for the 50 kibibyte one, if we do the same thing, we can clearly see the face is blurred. And that means the left-hand side one the 7.1 megabyte one has more pixels per row and more pixels per column compared to the right-hand side one, and hence it has a better image quality. Well, let's come back to the slides. We just saw two different photos taken at the same place with different camera sets. However, this leads us to the question, how does computer know how many pixels per row and how many pixels per column of these two images are? And also, how does computer know what color depths are used in the following four images, so it will make sure it displays the images properly. It understands what the data means. Well, we have to store additional data for each bitmap file, which is called header, highlighted in red here. So a bitmap file has a header containing metadata which defines the color depth and the resolution to help the computer display the rest of the image properly. So for the image file itself, there will be a section of header which has nothing to do with the image itself, but it stores some data about the image. Right. Let's have a look on this quick summary between bitmap files and vector graphics. And I'm going to take a quick test of you after this slide. So the bitmap graphics, what they're made of is made out of pixels of different colors. And vector graphic is made out of object, lines, equations, and calculations. What can be added to bitmap files? Individual pixels. What about vector graphics? Individual objects. What is the file size? Bitmap graphics is usually large as computers store details of every pixel. The vector graphics, on the other hand, is small as a computer stores details of objects, like the lines equations, the center of the circle, and the radius, and so on, which do not require much memory. What happens when they resize? Bitmap graphics owe lots quality, but vector graphics do not lose quality. Bitmap graphics looks real, and vector graphics looks not real. Many of them look like cartoon images. The native formats, the software can read the bitmap files .bmp or other common formats like JPEG, GF, TIFF, and PNG. And vector graphics, the common format is .svg, actually .pdf is also vector graphics. For the processing power, the bitmap files use less processing power than vectors because the screen is also made up of pixels. And if we display pixel images onto pixel screen, and it will be easier. But on the other hand, vector graphics is used more processing power than bitmaps, as lines and equations has to be calculated each time we display the image onto the screen. And what can be grouped? Individual elements cannot be grouped, and vector graphics, the individual elements can be grouped. And finally, last one, the quality of bitmap graphics are less precise than vectors. And on the other hand, vector graphics images are more precise than bitmaps. Well, I'll give you 10 seconds and then I'll go a quick recap on the summary slide. Let's get started. Vector graphics is made out of, and bitmap is made out of, well, lines and shapes and pixels. What happens when resize? Vector graphics get, the quality is the same. Yeah, and bitmap will lose quality. And vector graphics looks a bit, a bitmap. Well, vector graphics look a bit like cartoon images, but on the other hand, bitmaps look real. Native formats, vector graphics are, just think of one that I just taught you previously, which is .svg, perfect. And bitmap, we've got .img, .jpeg, and .bmp. And finally, advantages of vector graphics and bitmap. Vector graphics are more, the file size is smaller, and the bitmap it uses less processing power. Right, how many of you did it all perfectly done? Right, in the end of this video, let's go through an exam style question. The image is scanned with an image resolution of 1024 times pi 12 pixels and a color depth of 8 bits per pixel. Calculate an estimate for the file size, giving you answers in megabytes, and show your working. You can pause the video here and work out the answers on a piece of paper. Well, don't use a calculator because it's not allowed in the exam. Right, I'm suppose you have tried it, and let's go through it together. So we have 1024 pixels per row and 512 pixels per column, and the color depth is 8 bits per pixel. As we know that 1 byte is 8 bits, so in order to change this one to bytes, we need to divide it by 8, and then to kilobytes, we divide it by 1024 again, and then to megabyte, we divide it by another 1024, and this is the overall equation. The way I'm written it like this, because we can cancel the terms on this fraction straight away, instead of calculating it and then cancel it in the end. So now we can see the numerator got a 1024 and the denominator got a 1024 as well. It will cancel out. And also the numerator got an 8 and the denominator got an 8 will cancel out. And then finally the 1024, which is 2 times 5112. So if we divide both the denominator and numerator by 512, this will get 1 and this one will get 2, which means the final answer would be 0.5 megabytes, which is shown on the mark scheme exactly, 0.5 megabytes. Did you get this one correct? Well, that is the end of this video, and in the next video we're going to talk about the quality of sound and how sound is being represented in the computer system. Well, I hope you like this, and if you like this video, don't forget to give a thumb up and subscribe. Well, I'll see you next time.